In this video, we're going to look at more improper integrals, and these are improper integrals where the integrands have infinite discontinuities. And remember what that means. That just means the function has a vertical asymptote, or its graph has a vertical asymptote somewhere on this interval, the interval that we're integrating over. So if I look at this integral and somebody says, Miss Townsend, please evaluate this integral for me. On the surface, I might think it's just a regular integral. I'm just integrating from a to b. I've got a constant here and a constant here. And I might be tempted to just use the fundamental theorem of calculus. But I notice my integrand is an x times a natural log of x minus 2. And it's probably been a while since pre-calculus, but natural log of x looks like this. X equals 0, or the y-axis, is a vertical asymptote for natural log of x. So when I replace the x with an x minus 2, that's going to shift the whole graph over 2 units. Instead of having a vertical asymptote at x equals 0, we're going to have a vertical asymptote at x equals 2. Now, this shifted over 2 units is not the same as that function times x. But if I take values that look like this, and I multiply them by x values, let's say between 2 and 3, the negative y values that were originally here are just going to be steeper. They're just going to be multiplied by some number between 2 and 3. And then the y values over here, or the y values on this y equals natural log of x graph that have been shifted, when I take those and I multiply them by x, and x is somewhere between 3 and 4 and 5, it's just going to make everything steeper. So this is really asking about this unbounded area over here. It's all of the area between this function and the x-axis between x equals 2 and x equals 4. And notice that this is unbounded because we've got that infinite discontinuity or vertical asymptote. So this is the area we're interested in. I've got this piece and this piece. This piece is fine. That's just a proper integral over there if I were to evaluate the integral from 3 to 4. But over here we have a problem. We have a problem at x equals 2. Now, since the problem occurs at the lower limit, all we have to do, or lower bound, lower limit of integration, all we have to do is write this as a limit and evaluate the integral. I know a lot of students see this picture and they immediately want to split it up into 2 integrals, like that one and that one. You don't have to do that. We're going to write this as a limit because the problem occurs at x equals 2. Since it occurs at the lower bound, I'm going to replace that lower bound with a and let a approach 2. Everything else stays exactly the same. And remember, this is well defined. If a is not 2, a is some number a little bit greater than 2, this is just a normal integral. I can apply the fundamental theorem of calculus to this. So what this is going to give me is a net area between the function and the x-axis. So let's say a is right here, between a and 4. And the fundamental theorem of calculus applies to that interval. We're going to get that area up there minus that area down there. And then the question becomes, what happens to that difference? What happens to this area minus this area as a gets closer and closer to 2, turns out from the right? Well, to figure that out, I need to first find that blue area as a function of a, and then let a go to 2 from the right, and then we'll see if it approaches a finite value. Okay, so we did our first step. Remember, our first step is always to write the improper integral as a limit. It's a limit of a proper integral. And then we evaluate that proper integral, this right here, using the fundamental theorem of calculus. Okay, so you know, some students can get caught up on this step. Make sure you know how to write an integral with an infinite discontinuity as a limit. And then some students can get caught up on this step. We have to remember how to evaluate this integral. I'm just going to keep writing this limit. I want to keep everything nice and equal. Not really doing anything with it. And then think about what we would have to do over here to evaluate this. The first thing I ask myself is, do basic rules apply? And they don't. I've got a product. I've got a product of an x and a log function, a logarithmic function. So I definitely don't have a rule for that. Next, I could ask myself if u sub applies. Well, I could let u equal x minus 2, but then du is dx, and then we don't have anything for this x over here. I mean, we could do the change of variables, but it actually wouldn't get us very far. So if basic rules don't apply and u substitution doesn't apply, we're going to do integration by parts. And remember, with integration by parts, if there's a log function in your integrand, that's probably your u. So we're going to let u be natural log of x minus 2. We're going to calculate the du, that's the derivative times dx, and dv up here is everything else. Remember, with integration by parts, this is the integral of u dv. dv is x dx, and we will anti-differentiate x dx, add 1 to the exponent, divide by the new exponent to get v, and then take the derivative of natural log of x minus 2. So we get 1 over x minus 2 is a derivative of log of something, is 1 over that something, it's 1 over the function inside, times the derivative of the inside by the chain rule. And the derivative of the inside is just a 1. So we've got, this is our derivative, and then don't forget to multiply by dx to get the differential. Now, according to integration by parts, the integral of u dv is uv minus the integral of v du. So, still got more work to do over here. I have u v minus the integral of v times du. I put that x squared in the numerator here. And we have to evaluate this from a to 4, and we also have to evaluate this from a to 4. Once we decide how to handle this. Okay. Well, to simplify this, there are a couple of options. We can add a well-chosen 0 in the denominator, so that whatever's in the numerator, so that whatever's in the numerator will cancel with that x minus 2 in the denominator. That's a slick trick, and I really like that trick. But most people probably wouldn't think of that. Since most people wouldn't think of that, I think I'm just going to use synthetic division. So I've got a polynomial, it's a second degree polynomial, and I'm dividing by a first degree polynomial. So the easiest way to divide those two polynomials is using synthetic division. So I've got p of x divided by d of x, and p of x is x squared and d of x is x minus 2. Okay. For some reason my camera is having trouble focusing right now. Alright, there we go. It's a little bit better. Remember, whenever you do synthetic division, you need all of the powers of x, starting with the highest power of x that you see there. I've got an x squared, so I'm going to need to add an x term. We let the powers of x go down by 1, so that's x to the second, now I need an x to the first, and then I need a constant term, that's an x to the 0. there isn't one, so we're just adding these placeholders, 0, x, and 0. And we need this to go in descending powers of x as well, and it already does. We've got an x to the first and a constant, which is like a constant times x to the 0. Okay, so we've done that. Now when you do synthetic division, the first thing you do is you take the denominator and you set it equal to 0 and solve for x. So we get x equals 2. That goes in this little box over here. And then the coefficients of the numerator get listed to the right of that. So we've got an implied 1 there, a 0, and a 0. So then we bring down the 1. Then you multiply those two. I get 2. And then you add. And then you multiply. And you add. Okay. Now that last number is your remainder, and these are the coefficients of the polynomial that's left after you divide by the x minus 2. Now the polynomial in the numerator was a second degree polynomial. It started with an x squared. When I divide something that's, when I divide a second degree polynomial by a first degree polynomial, the power goes down by 1. The power is going to go down by whatever the degree of this polynomial is down here. Since I'm dividing by a first degree polynomial, it's going to go from 2 to 1. So these are the coefficients of a first degree polynomial. So this is the coefficient of x to the first, and that's the constant term. So this is our quotient. It's x plus 2. And it may have been a while since you've done this. Whenever you're dividing a polynomial by another polynomial, which we're going to call the divisor, you get a quotient plus the remainder, which is 4, over the divisor, which is x minus 2. So that's quotient plus remainder over divisor. And if you're a little rusty on this, that's okay. You might want to look up dividing polynomials, just in general, or dividing polynomials with synthetic division, which is what I just did. So we set the divisor equal to 0, solve for x, put that there, list the coefficients of the polynomial in the numerator here, bring the first one down, multiply, that number goes there, and add. Multiply, that number goes there, and add. Then these are the coefficients of your quotient. This is just this quotient's 1 degree less than this. That was x squared, so this is going to be x to the first. And then we'll have the remainder, which is a 4 over the divisor. Okay, so now we are ready to finish our anti-differentiation. It's actually pretty uncommon to have to do that in the middle of an integration by parts problem. But that's okay, we got some extra practice. Extra practice is always good. So that 1/2 is still there. And this x squared over x minus 2 simplifies to x plus 2 plus 4 over x minus 2. All right, now we can finish anti-differentiating that and apply the fundamental theorem of calculus. We could apply the fundamental theorem to this term. We could plug in 4 and a and subtract, but I think I'll finish this first. So I use a power rule here. That's an x to the first. So we add 1 to the exponent and divide by the new exponent. I've got a constant there. The antiderivative is a constant times x. This is a very simple u sub. If u is x minus 2, du is dx. So this is a 4 over u du. So we end up with a 4 times the natural log of the absolute value of u plus c. We don't need the plus c because it's a definite integral. Now if you're not sure about that, you should pause this video and do the u sub and make sure you get the same answer. Since u is so simple, since its derivative was just 1, I felt like I could do the u sub in my head. So we're going to do this, and then it needs to be evaluated from a to 4. And don't forget, we're taking the limit of all of this. As a approaches 2 from the right in a little bit. Okay. Having a little bit of trouble with my black Sharpie. I'm going to use a different pen. All right. So we have the limit as a approaches 2 from the right of all of this. And I think I'll simplify first before I apply the fundamental theorem. So I've got 1/2 x squared, natural log of x minus 2. If I distribute the 1/2 to all of these terms, I've got a negative 1/2 times a 1/2, so it's negative 1/4 x squared. Negative 1/2 times 2 is negative 1 times x, and then negative 1/2 of 4 is negative 2. And I could stop here, but I think I want to simplify my work as much as possible. So I think I'm going to group these two guys together. Since they both have natural log of x minus 2 in them, I'm going to write them together out here. So we're going to have 1/2 x squared minus 2. And I'm factoring out the natural log of x minus 2. Now check and make sure that you agree with that. If you take 1/2 x squared and multiply it by that, you get that. And if you take the negative 2 and multiply it by that, you get that term. So I'm just putting those two pieces together over here because it might make taking the limit at the end easier. Don't forget, we still have to plug in a and 4 and subtract the fundamental theorem. Okay. So that was a tougher integration than expected. That's all right though. Good practice. Got an exam coming up. I need to review those 8.1 techniques. All right, so let's plug in 4. 4 squared is 16. Half of 16 is 8. 8 minus 2 is 6. So we're going to have 6. Natural log of 4 minus 2. 4 minus 2 is 2. Minus 1/2 or 1/4 of 16. 4 squared is 16. 1/4 of 16 is 4. And then we're subtracting another 4. Then substitute in x equals a. So we have 1/2 a squared minus 2 times natural log of a minus 2 minus 1/4 a squared minus a. All of that we need to simplify. We need to take the limit of this entire quantity as a approaches 2 from the right. Now that's just a constant, so that's not going to change. We're just going to have 6 natural log of 2 minus 8. And then as a approaches 2 over here, notice we get 2 squared. 2 squared is 4. 1/2 of 4 is 2, so we're going to have 2 minus 2, which is 0. So this guy is approaching 0. And as a approaches 2 from the right, remember our picture, so we're approaching 2 from the right, that log is a large negative number. The limit of natural log of something is that something approaches 0 from the positive side. So when I'm taking the log of a really tiny positive number, the y values go to negative infinity. Now, this graph looks a little different. It looks more like this. But as I'm approaching 2 from the right-hand side, this is log of something tiny and positive, so this is going to negative infinity. So this is a 0 times negative infinity indeterminate form. Now this part is continuous. I can just plug in 2. So I've got 1/4, and then 2 squared is 4, minus a, as a approaches 2 from the right, so that's just going to be a 2. And plus this, the limit of this guy over here. That was a constant. We were able to take that limit. Provided these limits exist, this is equal to this limit. And I think I'll leave my minus sign out here. Now, in order to address the 0 times negative infinity indeterminate form, we have to use L'Hopital's rule. Now you've got some options. You can either put 1 over this in the denominator, and then you'd have a negative infinity over infinity indeterminate form. Or you can put 1 over this in the denominator. You've just got to change it a little bit so that it's written as a fraction. If you put 1 over this in the denominator or 1 over this in the denominator, you're going to get either 0 over 0 or plus or minus infinity over infinity. And that's what we want. That's what we need in order to apply L'Hopital's rule. I think I'm going to choose to put my natural log in the denominator. I know it looks kind of bad. But I think that's ultimately going to make it simpler. So this is natural log of a minus 2, and it's raised to the negative first power. All right. Now, as a approaches 2 from the right, the numerator approaches 0. And this is 1 over something that's going to negative infinity. So 1 over something really large is something really small. So it's a 0 over 0 indeterminate form again. Now, by L'Hopital's rule, this limit is equal to another limit. And all this other stuff should come down as well. So we've got 6 natural log of 2, minus 8 minus 1, that's minus 9. Minus 9 minus 2 is minus 11, minus this limit over here. Take the derivative of the numerator. So you'll have 1/2 times 2, you bring that power down, is 1, times a to the 1 less power, so that's a to the first, times the derivative of the denominator. Now I have natural log of something raised to the negative 1, so I'm going to have to use the chain rule twice. The outermost function is this negative 1 power. This is like a function to the negative 1. The derivative of a function to the negative 1 is negative 1 times that function to the negative 2 times the derivative of the inside by the chain rule, and the derivative of the inside is 1 over the inside function of the log, because the derivative of a log is 1 over the inside function times the derivative of the inside of that. The derivative of the inside of that is a 1. So we're done. Okay, now the question is it still an indeterminate form? Well, it's a little bit hard to tell. So I'm going to do a little bit of algebra on the next page, and hopefully it won't be an indeterminate form anymore. So we're here. We've got 6 natural log of 2 minus 11 minus the limit as a approaches 2 from the right of this guy. Now I am dividing by a fraction here, so we can multiply by the reciprocal. Actually, let's write this as a fraction as well. So I've got negative 1 over natural log of a minus 2 squared, all multiplied by a minus 2. Oh goodness, I think it got worse. So we're going to take this, we're going to flip it and multiply. So we have a times negative natural log of a minus 2 quantity squared times a minus 2. Oh, I think that got worse. It got much worse. I'm sorry, guys. My intuition was off. You know how that is, don't you? Got a negative times a negative, that's a positive. and I've got an a times a minus 2. If I distribute that, I'm going to have a squared minus 2a times natural log of a minus 2 quantity squared. That was much worse than what I started with. Remember, we started with this guy back over here. I'm making things worse. So I think I'm just going to go back to this. I want the limit of this product, and instead of putting 1 over the log in the denominator, I'm going to put 1 over this polynomial in the denominator. And I'm going to hope that that's going to be simpler. So we'll have minus natural log of, or the limit as a approaches 2 from the right of, I'm leaving the natural log of a minus 2 in the numerator, and I'm putting this in the denominator. So I've got 1 over 1/2 a squared minus 2. Now, if you don't believe me, if you take that and you flip it and multiply, whenever you're dividing by a fraction, remember it's multiplying by the reciprocal. If you do that with this, I guarantee you, you're going to get this times that over 1. So that's going to be that right there. So we went on a little detour, and that's okay. Sometimes we take detours in math. Turned out it was a detour, but we didn't know. So it's perfectly okay. So now let's look at this. As a approaches 2 from the right, this is still approaching negative infinity, and this is still approaching 0. So as a approaches 2 from the right, I've got this is approaching 4, half of that is approaching positive 2, and this is slightly larger than 2. So that number that's slightly larger than 2 minus 2, and that's going to be a tiny positive number. 1 over a tiny positive number is a large positive number. Okay, so we're going to use L'Hopital's rule on that. And to make the differentiation easier, I'm just going to rewrite that as a power, use the chain rule. I wanted to show you guys this. I didn't want to start my video over. I wanted to show you that sometimes this is exactly what happens. Sometimes you make a mistake, or your intuition's wrong, you try something and it doesn't work. That's okay. Then you do something else. Okay, by L'Hopital's rule. So we're going to put a little h over equals sign because we're applying L'Hopital's rule. The limit of this is equal to the limit of the derivative of the numerator over the derivative of the denominator. Our hope is this is going to make things simpler. Derivative of the numerator is 1 over a minus 2, because the derivative of log of something is 1 over the function inside times the derivative of the inside. And the derivative of the inside is 1. Okay, so here I've got to use the chain rule. Again, here's my inside function. The outermost function is that power function. I'm taking a function and I'm raising it to the negative 1. The derivative of a function to the negative 1 is negative 1 times my function to the negative 2. My function in this case is 1/2 a squared minus 2 times the derivative of the inside. Derivative of 1/2 a squared is 1/2 times 2, which is 1, times a to the first. Okay, and our hope is that this is not indeterminate. We will see. We will see shortly, won't we? At least we got rid of the log. That's a good sign. The other way, we're getting higher and higher powers of logs. We're like, I don't think that's what we want. It's going to make it much worse. Okay, so this is actually a fraction in the denominator. I've got 1 over a minus 2 over, well, I've got this negative. I think I'll pull that out here now. This over this squared, 1 over that squared, times a over 1. So I could multiply these straight across and it's going to be a different fraction. I had no idea it was going to be as much of a headache. It's just making that x into an x minus 2. It changed everything. Let's see. All right. So if I've got this divided by this fraction, I'm going to leave the one in the numerator alone. Take the one in the denominator, flip it, and multiply. All right, so I've got 1/2 a squared minus 2 quantity squared over a squared minus 2a. Question is this still an indeterminate form? If I take the derivative of the numerator now, or excuse me, if I plug in a equals 2 in the numerator now, I still have 4 times 1/2, which is 2. 2 minus 2 is 0. So I've got 0 squared. So I've got 0 there. And 2 squared is 4, and 2 times 2 is 4, so I've got 4 minus 4, so that's also a 0, so it's still a 0 over 0 indeterminate form, but at least there are no logs in it. I got polynomials. That's encouraging, because we know eventually we'll get a constant when we take the derivative of a polynomial. So let's apply L'Hopital's rule. All right, according to L'Hopital's rule, the derivative of this is, or excuse me, the limit of this function is the limit of derivative of the numerator over derivative of the denominator. So I've got a function squared. Derivative of a function squared by the chain rule is 2 times the function times the derivative of the inside. And the derivative of 1/2 a squared is 1/2 times 2, that's a 1, times a to the first. And we're dividing all of that by the derivative of the denominator. And the derivative of the denominator is 2a minus 2. And I see that some 2's reduce. That's nice. So I can factor out a 2 up here. And factor out a 2 here. I wrote an a, I'm factoring out a 2, not an a. So the 2's reduce. And now I ask myself, is this still an indeterminate form? Well, as a approaches 2, that's a 2 times something that's approaching 0. So my numerator is 0. Is the denominator still 0? It's not! That's a great thing. So this is a 0 and that's approaching 1. What's 0 divided by 1, guys? I hope you said it's 0. Yes, it is. This is going to 0. So turns out the limit is this. 6 times natural log of 2 minus 11. And you say, Miss Townsend, what were we doing again? It was such a long time since we started this problem. I agree. I really do. Let's go back to the beginning. We were trying to evaluate this integral. And it was improper because we had a little problem at x equals 2. The function goes to negative infinity as x approaches 2. So we wrote it as a limit, and we said let's find the area under the curve from a to 4, and then see what happens to that area as a gets closer and closer and closer to 2 from the right. I said, okay, well, in order to find that area, we're going to have to use the fundamental theorem of calculus. And in this case, with the fundamental theorem, we had to use integration by parts. Then we had to do this dividing polynomials with synthetic division so that we could anti-differentiate it. We wrote that like this. That's nice. All I have to do is anti-differentiate using a couple basic rules and a very simple u-sub. And now finally, I can do a little algebra and apply the fundamental theorem of calculus. So we plug in 4, we plug in a, and we subtract. Okay, so we're there. We have written the integral as a limit and then evaluated the proper integral to find the area as a function of a. And now we're at the step where we say, okay, what happens to this thing, this area, as a approaches 2 from the right? So we needed to evaluate the limit. Okay, that's a constant. That approaches a constant, so we were good over there. We just needed to evaluate this limit. It was a 0 times negative infinity indeterminate form. So we tried rewriting it as a 0 over 0 indeterminate form. It turned out that that made it worse. I noticed the natural log that I used to have in the numerator was now a natural log of a minus 2 squared. It was getting worse. So I said, okay, that was a detour. Let's go back to where we started, and instead of making it in a 0 over 0 indeterminate form, let's make it a negative infinity over infinity indeterminate form. So we did, and then we applied L'Hopital's rule, and after applying L'Hopital's rule, we still had a problem. We have a 0 over 0 indeterminate form. So we applied L'Hopital's rule again, and it turned out we finally got rid of the 0 over 0 problem, and we got this. Say, okay, Miss Townsend, what does that mean? This is the net area. This net area that we shaded earlier, the area between the function and the x-axis between x equals 3 and x equals 4, that area is counted as positive. And this area over here is counted as negative. And when you take this area and you subtract this area, I know it doesn't look like it from my picture because my picture is not to scale, but it turns out that that area is greater than that area, and this red area, as a gets closer and closer and closer to 2, that area is approaching 6 natural log of 2 minus 11. Now, I think I just said that that was guaranteed to be positive, but that minus 11, yeah, I'm not sure if that's positive or not. But the net area, the area above the x-axis minus the area below the x-axis, that's equal to this. And we say that that is the value of our improper integral, the integral from 2 to 4 of x times the natural log of x minus 2. And we also say this integral converges. And it converges to that number. All right, that was a very long example. I was going to do 2 videos or 2 examples in this video, but that took us 38 minutes. So I think I will save the next example for another video. Thank you for your patience, guys. I hope reviewing all those concepts was good for you.